right, so I'm going to finish up problem 7. So when we do this, the value that we get is equal to, let's see, so it is equal to, the gas will be traveling at this particular temperature, 3 times 10 to the 6th, that's, it got a little skewed there, is traveling at 271.9 kilometers per second. All right, so kilometers per second. So we'll just round that to, 272 kilometers per second. All right, so where does that get us, right? That's going to be the speed of the gas. And see, the part that they really want you to use here, and let me get a new screen here. The part that they want you to use is knowing that value, 272, that's the speed of the gas. How far from the sun in solar radii would that gas reach an escape speed? Okay, so here's the equation that works out to. Okay, so remember, the key thing here is from the surface of the sun. Okay, from the escape speed from the surface is equal to this. Remember, we did this before. It's 618 kilometers per second. All right, and we found that the gas. So this is the velocity of the gas. So we just derived that the gas at 3,000 Kelvin is traveling at approximately 272 kilometers per second. All right. So how far away from the sun, from the center of the sun, would it have to be for that to reach the escape velocity? And there's actually an equation for this, and so the way that would work is the escape speed from, I don't know how to, the escape speed from some r, from some, we'll use capital R, from some r is equal to, all right, so this is the way it works. You put the escape speed from the surface of the sun, which of course was 618 kilometers per second, all right, times the square root, all right, again, I'm just getting this from the chapter itself, so it's going to be times one solar mass, one solar mass. So I'm just going to put mass of the sun, which is just going to be 1 divided by the distance from the sun, r, in solar units, right? In solar units. And what I mean by solar units, this is really solar radii, right? So we're really going to solve this for r. We're about to do that. All right. So now, what is that equal to? So what we do is we set that equal to the velocity of the gas, right? At that temperature. So at that temperature, the velocity of the gas, we worked this out already, is 272 kilometers per second. And of course, both sides. So this is really what our equation is. Both sides have kilometers per second. They cancel, of course, and so you can actually work this out. Let's get a bigger screen here, and. Sorry. All right, so that becomes, let's see, so it would be, so it's really going to be just one 1 over the square root of the r in solar radii. All right, so this is, whatever the mass of the sun is, whatever this number comes out to be, it'll be, sorry, not the mass of the sun, the radius of the sun. So if the number comes out to be greater than 1, then, and of course it's going to, but if it comes out to be greater than 1, then you take that number, you multiply it by the radius of the sun, right? So anyhow, and this is of course times that 618, and we've already canceled, of course, the kilometers per second, because that, and this is equal to 272. All right, and so just rearranging this equation, right? I think you could probably see it becomes 1 over the square root of, I'm just going to use r here. Just remember that r is in solar units, and so that's equal to 272 divided by 618. Right, 618. That's supposed to be a 6. So 272 divided by 618. So really, the whole thing comes down to this, and we really just want to solve for r, right? So I'm going to bring the square root of r over to the other side of the equation. I'm going to bring this fraction over to the other side. So it's going to look like this. It'll be 618 over 272. And that's equal to, so that gets the r in the numerator, and then of course you just square both sides of the equation, right? So we just square both sides of the equation because we're solving for r, right? And so this is what r comes out to be. Remember, it's in solar radii, right? So it's going to equal 5.2 times the radius of the sun, r of the sun. So like if you wanted to know that number in kilometers, you look up the radius of the sun in kilometers, you multiply it by 5.2. And in other words, gas at this temperature, at 272, that's the speed. Gas at that speed, because the temperature is 3 million Kelvin, the gas is traveling at that speed. But if that gas ends up 5.2 times the radius of the sun, it'll leave the sun and never come back, right? So that's the idea. All right, let's do the next problem. All right, so the last problem, as it says here, so we're going to assume a constant luminosity. That's the rate at which the energy is flowing out of the sun. Calculate how much equivalent mass relative to the current mass of the sun, which of course is 2 times 10 to the 30th kilograms, the sun has radiated into space in the 4.6 billion years since it formed. How much hydrogen has been consumed, and how long will it take the sun to radiate the entire its entire mass into space? So this is part A and a part B. All right, so let's work on that. All right, so I'm setting this up. So they give us the luminosity is constant, so we're going to assume that. It's 4 times 10 to the 26 watts. 4 times 10 to the 26 watts is power, which are units of energy per second. So joules are the units of energy that we use in the standard international system. So power is energy divided by time. Rearrange that equation, you solve for the energy. So the energy is going to be the power, which of course is 4 times 10 to the 26 watts, times the time, which would be the number of seconds in a year. Okay, so this is the time. Now, this is t. So we have to figure out what the time is. So you take 4.6 billion years, you multiply it by 365 days. The years cancel, and then there's of course in one day there's 24 hours, the days cancel. 1 hour, there's 60 minutes, the hours cancel. 1 minute, there are 60 seconds. So you multiply 4 times 10 to the 4.6 times 10 to the ninth times 365 times 24 times 60, and you get, what do you get? Let's see, I get 1.45 roughly. That's supposed to be a 4 or 5 times 10 to the 17th seconds. 10 to the 17th seconds. All right, so now that you have that in seconds, you're going to put that in right here. All right, so we're going to do that right now. All right, so let's do this. I got to get a little room here. All right, so so the time, or I'm sorry, the energy, right? The energy is equal to. Remember, it's the amount of energy that's coming, the power that's coming off the sun. So it's and times the amount of time. So it's going to be 1.45 times 4. That's a 5 times 10 to the. Remember, we just calculated this. 10 to the 17th seconds. All right, 10 to the 17th seconds, and then we times it times the energy, which or the power, which is 4 times 10 to the 26th joules per second. And of course the seconds cancel, and that gives us the raw amount of energy. Okay, so over the course of 4.6 billion years. All right, so the amount of energy that's come from the sun in all that time is 5.8 times 10 to the 43rd joules, which is a tremendous amount of energy. And so if we use Einstein's famous equation, E equals mc squared, so now we know what E is, we're going to figure out what the mass is. All right, C, of course, is the speed of light. The energy has to be in joules, the mass has to be in kilograms. So the mass, this is really the problem, this is what we want to solve for. The mass is the energy divided by the speed of light squared. And all right, so here I've actually written it out. So we're solving for the mass, that the amount of mass that is turned into energy over the course of 4.6 billion years. So that that's the amount of time in seconds. 4.5 times 10 to the 17th. This is the luminosity of the sun, the amount of energy per second. So this is the total amount of energy in the last 4.5 billion years. And then of course we divide by the speed of light. The thing about it, the speed of light has to be in meters per second. We divide by the speed of light squared, right? Because E equals mc squared. And so when you do this, you get 6.45 times 10 to the 26 kilograms. And if you look it up, that's about roughly the mass of Saturn. So that's a huge mass. Saturn's a second largest planet in the solar system, but next to the mass of the sun, which is of course 2 times 10 to the 30th, it would that would be a tremendous amount of energy. A tremendous amount of mass, but the sun has a lot more mass to use. All right, so that will be that'll be it for these problems.